Um, and so, and at the end of class today, we're going to do the first quiz. Just it'll take 10 minutes or something. Okay, so last class. I introduced the three constant acceleration equations. And those are, the first one says V final is equal to V initial plus A times time final. The second one says P final is equal to P initial plus V initial times time final plus 1/2 AT final squared. And the last one says 2A times the quantity P final minus P initial is equal to V final squared minus V initial squared. And the meaning of these things is, you can think of it as initial means at time equals 0, and final means at time final. And I did one simple example problem, but I haven't gone through a set of steps for using these yet. So I'm going to start today by just going through a set of steps. I would recommend that at first, when you first start using this stuff, that you follow the steps pretty carefully. You know, once you get used to it, once you've done a lot of problems like this, you'll probably end up, you know, taking sort of shortcuts and stuff. But for now, I think this is a good way to make sure you don't skip anything. Okay, so here is a general set of steps. General steps for using the constant acceleration equations. So the first thing you have to do is make those choices. You know, I've talked already about choosing the position equals 0, the positive direction, and the time equals 0 instant. There's a fourth thing we have to choose here, and that's what instant is going to correspond to time final. Basically, when do you turn on the stopwatch, and then when do you stop the stopwatch? Okay. So the first one is choose. And there are four things you have to choose. A position equals 0 location. A positive direction. And by the way, these are both arbitrary. This doesn't have any bearing on whether or not you can do the problem. There are some choices you can make that make the math a little simpler or whatever, but those are up to you. The other two, the ones related to time, you have to pick right or you can't get the problem right. So you have to choose a time equals 0 instant. and you have to choose a time final instant. And these you have to choose right. So what are you using to make the decision about what those instants are? You want these to be instants where you're either given information or you're trying to find information. So if you're given information like the speed at a certain instant, or you're trying to find information like the position at a certain instant, then those are clues about what instance you're gonna choose for 0 and time final. So it's where you're given information and or where you're trying to find information. The second step, so now we have to figure out what variables we know and what variables we're trying to find. And if you look at the 3 constant acceleration equations, there's only a total of 6 variables that you have to deal with. So you might as well just always do them in the same order. So out of, so the 6 variables are time final, acceleration, initial position, final position, initial velocity, and final velocity. And you're trying to figure out what variables you know and what single variable you're trying to find. Trying to find. So the way I usually do it is I'll make a column of the things I know, a column, well, a place to write down what thing I want to find, anything that we're not given information about and we're not specifically asked to find doesn't go anywhere. Okay. So maybe you know that acceleration is something, initial position is something, initial velocity is something. I'd put the numbers, the values in there, and let's say that what we're trying to find is V final. Once you've figured that out, you can look for an equation that's going to work with these. So what does it mean for an equation to work? You're looking for an equation that has the variable you want, and all the other variables are known. So what's the deal with that? Like, look back at these equations. So with any one equation, you can solve for a single variable, right? You can't use one equation to solve for more than one variable. And so let's say we're trying to solve for V final in this first equation. We need to, so that has to be the thing we're looking for, and it has to be in the equation. And then all the other things in the equation have to be in the column of variables that you know. Otherwise, you can't do it. Okay. At least at the beginning, that's kind of the end of this process. Then you just solve for the variable you're looking for. Sometimes, though, after we get a little more used to this, there's this step 4 that you have to do sometimes. If there isn't an equation that works, so if no equation works, solve for another variable that you don't know. The best choices for these are usually time final or acceleration. And then try again. Because once you solve for this variable you don't know, then you have one more variable that you do know, and maybe now you can find an equation that'll work. Okay, any questions about that? Okay. Let's do an example. I don't think I did one with a car yet in this class, right? Just a ball rolling on a hill or something. What? We did? Did we also do a ball on a hill? Oh, we did the car just talking about the direction of acceleration and stuff. Okay, we're going to do one with numbers this time. So let's say that a car starts at rest. And is clocked going 30 meters per second. Let's see, how far would a car have to go to get up to 60 miles per hour? 100 yards? Is that too short? 200 yards? Okay, let's say 200 meters. So it starts at rest, it's clock going 30 meters per second, 200 meters away. So if we assume that this car has constant acceleration, what's its acceleration? We don't know that. So what's the acceleration? Okay, so let's just go through the steps carefully. Step 1, we have to choose a 0 position and a positive direction. And I'm going to draw a picture of this. So here's the car. It's going this way. It starts out here and ends up here where this distance is 200 meters. This point is A, this point is B. All right, well, first, once we choose our positive direction and 0 position, coming up with positions and stuff at the different instance is a lot like the problems we've done with the beach and the buoy and the boat or whatever, the house. So what do you want to choose as the zero position? Either A or B would be reasonable. Probably anything other than that would be unnecessarily complicated. Most people would probably pick A, but you don't have to. And what about a positive direction? Yeah, let's choose the direction the car is going. And so based on that, the position at A is what? 0. And the position at B is what? Yep, 200 meters. And we've also determined something else when we made those decisions. What is the velocity when the car is at A? 0. So VI is 0. And what's the velocity at B? Okay, and when we chose the positive direction, we learned that was the instant that we found out that the velocity at B is positive 30 meters per second. Because we know that the car is going this way. But if we had chosen our positive direction to be this way, the velocity at B would be negative 30 meters per second. Okay. So we couldn't put numbers to any of this stuff until we made those choices. So velocity final is positive 30 meters per second. Oh, well, I sort of gave it away by naming these V initial and V final. But what instant are we going to choose for our time equals 0? Well, you want to choose instance where you're looking for stuff or you know stuff. And the only places we know stuff are this instant and the instant where it gets to B. Okay? So one of those has to be time equals 0 and one has to be time final. And time equals 0 is always before time final, so that just determines, then we know what those choices are. Okay. Any questions about that, choosing the times? So time equals 0 is when the car is at A. Time final is when the car is at B. And now we can think about what we know and what we're trying to find. And I'm just going to go through the list in order. So time final, do we know that? No. Are we looking for it? No. If we can't find an equation that works, we might come back and use that as our sort of bootstrap variable to try to come up with enough stuff to solve. But if we can figure out the acceleration without finding time final, that's fine. So we'll leave it off. Do we know the acceleration? Nope, that's what we're looking for. Do we know the initial position? What is it? 0, yep. Do we know the final position? Yep, 200 meters. Do we know the initial velocity? Yep, 0. And do we know the final velocity? Yeah. And so for an equation to work, it needs to have A in it, because if it doesn't have A in it, you can't solve for A. And then everything else in it has to appear in that list in the known column. So you can just go through the equations one by one. That first equation, you always want to use that if possible, because it's the simplest one. You don't have any squares. You never have to deal with square roots or anything. But one says, so V final, we have that, so far so good, is equal to V initial, we have that, plus A, so that's good, times T final. And that's the problem. We don't know T final, and we already are looking for A, so that one won't work to solve for A. Second equation says P final is equal to P initial plus V initial times time final, and there's the time final again, so that one's not going to work. And so our last chance to have one that works says 2 times A, so it has the variable we're looking for, times the quantity P final minus P initial, so we're still in business, is equal to V final squared minus V initial squared. So that one works. Okay. So the one that we're going to use says 2A times the quantity P final minus P initial is equal to V final squared minus V initial squared. And I'm going to start filling these in. You're not going to have to do this for the whole semester, but for now, I want you to keep the units in your calculations, okay, just so you can see how this all works out. If you do that, then, so we're going to solve for acceleration, and you'll see that when we keep all the units in the calculations and multiply them and divide them and cancel them and everything, what you get is that acceleration is equal to some number with the proper units on it, meters per second squared. So this is sometimes a useful way to find mistakes that you've made. You know, if you get an answer for A and it's not in units of acceleration, something went wrong somewhere. It might end up, when you go back and fix it, it didn't change the numbers, but a lot of times it will change the numbers. Okay, so we'll plug in what we know. So we have 2 times A times the quantity, 200 meters minus 0, is equal to the square of V final. V final is 30 meters per second. We're squaring that. And then minus V initial squared. And so when we multiply the stuff on the left side of the equation, we get 2 times 200 meters times A is equal to 30 meters per second squared. I'm going to write that like this. So it's 30 meters per second times 30 meters per second. You have to square it all. And now you can divide both sides by m. You get rid of one of those meters. And the equation now, 2 times 200 says 400A is equal to 30 times 30 is 900 meters per second squared. And so now divide both sides by 400 and you get A is equal to 2.25 meters per second squared. Any questions about that? Okay, does it make sense that the acceleration is positive in this problem? Yeah, because the car is speeding up and the velocity is positive. So if it's speeding up and the velocity is positive, acceleration has to be positive. Let's also, given the stuff that we know now, let's draw a little sketch of position versus time. Okay, so what do we know? Well, we don't know the time, so we'll say that we know that 0 time is when it leaves the point A. Let's say this is the time when it leaves when it gets to the point B. The position when time is equal to 0 is this. Okay, so this is time, this is position. So at time equals 0, you're at 0 position. The other position we know about is 200 meters. And at the instant you get to point B, you're at position 200 meters, so I'll make a point there. What's the velocity at time equals 0? 0, yep. So we know that the slope at that instant is that, you know, it's a horizontal, the tangent line is horizontal at that instant. What's the velocity when we get to B? 30. And for sketching this, all we need to know is that that's positive. Okay. And what's the acceleration? 2.25, it's positive. So is that concave up or concave down? Up. And so it's going to look something like this. Any questions about that? Okay. So now, the most important motion with constant acceleration is free fall, which I'm going to use as synonymous with projectile motion. So I'm going to call something free fall, whether it's on its way up being launched or launched horizontally. So free fall, projectile motion. It's also known as ballistics, if you've ever wondered what ballistic means. If you were really accurate about what it meant for someone to go ballistic, like you went ballistic, that would just be like falling flat to the floor. And when an object is first not touching anything, and second, air resistance is negligible, and I'll talk a little bit about that assumption. The acceleration is down at 9.81 meters per second squared. Okay, so that's if something is falling, right? When something falls, it falls down. The acceleration is down. What do you think the acceleration is? This is a trick question. What do you think the acceleration is when you throw something up in the air and it's on the way up? What's the acceleration? Positive? 9.81 meters per second squared up? Yes, it's still this exact same thing, okay? So, and when you get confused about that, I think the main reason a lot of people often get confused about that. I think usually what you're messing up on is your brain is telling you that acceleration is really what velocity is, okay? Acceleration is this different thing that tells you how velocity is changing. It's harder to visualize. But think of it this way. So if you take an object and you throw it up into the air, okay? So the instant this leaves my hand, it's in free fall, projectile motion, okay? So right after it leaves my hand, when I throw it up into the air, what's the direction of the velocity? Up, right? Is it, as it goes up, is it speeding up or slowing down? Slowing down, so what's the direction of the acceleration? Down. It has to be for it to slow down. So then it slows down until it gets to its highest point, and then it starts speeding up going down. So on the second part, when it's on the way down, what's the direction of the velocity? Down. It's speeding up. That means acceleration is also down on that part, okay? So the acceleration is down. No matter, no matter, no matter, no matter what part of the flight it's in. This, this could be the end of my whole body is coming apart. No matter what part of the flight it's in. Okay. So when can we neglect air resistance? In space, yes. So yes, that's exactly right. But you know, all of the free fall calculations that we're going to be doing are meant to simulate motion outside of a vacuum, right? I mean, nothing happens in a vacuum really that we care about. So when can you get okay results by treating a thing like it's in a vacuum, I guess is the question. Okay. And the answer is when the object has a large mass and or it has small size and or the shape is aerodynamic and or it's moving slowly. Okay, so if you think about what those don't give any like rules for what you're gonna what you're thinking of as acceptably massive or small or whatever, but these are just like the trends. If everything else stays the same and the mass gets bigger, as the mass gets bigger, air resistance becomes less important. If everything else stays the same and the size gets smaller, air resistance gets less important. If it gets more aerodynamic, same thing. If the motion is slower, same thing. So like some examples are, if you, you know the shot put in track? So it's the giant people throwing steel balls that are like this big, and they weigh 16 pounds, okay? Well, that's a very dense object, very massive for the size. So that's sort of good as far as 1 and 2 go. And then also, it's not being launched out of a cannon or anything. It's being thrown, and it's heavy enough that you can't throw it that fast. And so if you had the speed of one of these shots just as the person released it, and you assumed that that motion was happening in a vacuum and did a calculation of its flight, your answers for the whole flight would be just about perfect. You know, air resistance is so unimportant in that motion because you have something with a lot of mass, not very big, not moving very fast. Okay. But if you had, I mean, at the extreme, like imagine a feather that you release from rest, okay? You know that when you release it, it's just going to flutter down slowly. If you treated that as having no air resistance and used the free fall approach, all your results would be terrible right from the start because the feather has tiny mass spread over a relatively large size. It has a big surface area. There's a lot of area to catch the wind. And I guess the other ones, the shape doesn't really matter. It's never moving very fast. But just these are so against it that the results are terrible, you know. Okay. Well, let's do a calculation. Okay, so let's say you're standing on a bridge and you don't know the height of the bridge. And so you check very carefully to make sure no boats are coming under the bridge. If you really do this, that's a super important step. And so here's the bridge, here's the water, and you drop a rock down toward the water, okay, and time how long it takes. If the rock takes 1.2 seconds to hit the water, what's the height? Okay, well, let's just go through the steps. This is a constant acceleration problem, so we're going to use those same three equations. The one thing that you have going for you in any free fall projectile motion problem is you know the acceleration before you start. You never have to solve for that. So first, we have to make those choices. What do you want to choose as position equals 0? So you could, there are probably two choices people would tend to make. One is you call it 0 where the rock is released. And the other one is you call it 0 at the water. Either one of those is fine. I'm going to put the 0 here for this problem. I guess I usually do green for that. Okay. And what do you want to call the positive direction, up or down? Either one's fine. Down. Okay. Like almost nobody would ever choose that, but it's fine. It won't mess up. We can totally do it. And what we're trying to figure out is the distance between these, you know. And now we have to choose the instance. What's going to be our time equals 0 instant? Yep. So let's say it's the instant that it's released. And our time final instant? Yeah, that's right. So usually we just have to choose an instant. This time we actually know what the number is. And that's when it hits the water. So now we can start to think about what variables we know and what variables we want. So time final, do we know that? So time final is 1.2 seconds. Do we know acceleration? Okay, and the sign of that is going to depend on our choice of positive direction. So is it positive 9.81 or negative? Normally, like if you approach this like every other person on Earth, your positive direction will be up, and so acceleration will be negative. Okay. But we chose positive direction down. Gravity makes things accelerate down. So this time our acceleration is positive 9.81. Now PI, do we know the position when time is equal to 0? Yeah, that's the position when the rock is released. Do we know what that is numerically? That's what we're trying to find, exactly. So, right. And one thing that's sort of interesting about this is, what if we would have chosen our 0 position to be up there? Then we would have known that our P initial was 0. But instead of knowing P final, like in this case, that would be what we're trying to find. Okay. Do we know P final? 0, yep. Do we know the initial velocity? 0, yep, it's released from rest. And so at the instant you let go of it, it's 0. And do we know V final? We don't know that. And it's a common mistake, an easy mistake to make, to think, well, yeah, it hits the water and the water stops it, and so the velocity is zero. But this stuff only holds during free fall. So the instant the rock touches the water, these equations don't work anymore. So when I say what's the velocity when it hits the water, what that really means is what's the velocity the instant before it first contacts the water. Okay. All right, so we don't know V final, but if we can get PI without it, we're happy with that. So do any of those three constant acceleration equations work? So the first one says V final. Okay, that one already isn't going to work because we don't know V final and we're trying to find PI. So the V final equals V initial blah, blah, blah equation won't work. Okay. The second equation says P final, we're okay with that, is equal to P initial. That's good. That's what we're trying to find. Plus V initial times time final. We know both of those. Plus 1/2 A TF squared. And we know all that. So this is the one we're going to use. P final is equal to P initial plus V initial times time final plus 1/2 A T final squared. And so now filling this in, we get 0 is equal to P initial, that's what we're looking for, plus 0 times TF is just 0, plus 1/2 times negative 9.81 meters per second squared. Not negative, thank you, I'm just used to writing that. Thank you. Times time final squared, 1.2 seconds squared. And so P initial is equal to, so basically I added that uglier term or subtracted it from both sides and then switched which side was which. So now this PI is over by itself on the left and we have negative 1/2 times 9.81 meters over seconds times seconds times 1.2 seconds times 1.2 seconds and you get cancellations of all the seconds. The units you're left with is meters, and that's good. That's what we want for position. And you get an answer of negative 7.06 meters. Okay, so does it make sense that we got this negative answer for position? Yes, because our 0 position is at the water, and the positive direction is down. So negative positions are telling you how far above the water you are. Okay, and so the answer is the bridge is 7.06 meters high. Okay, what if you came to a bridge, you wanted to know how high it was, and there were no boats coming, but there wasn't a rock there, there was a marshmallow. Okay, what So you do this calculation. Are your results going to be good? No, because a marshmallow in that same fall would develop a lot of air resistance. And so your calculations that are assuming there's no air resistance at all would be really far off from what really happens with this marshmallow. Okay. So the marshmallow would take an extra long time to hit the water, and you'd estimate that the bridge is way too high, way higher than it is. Okay. Any questions about that example? Okay, let me show a cool video. It'll just take a couple minutes, but it has to do with this air resistance thing, and it's just like, even no matter how convinced you are that without air resistance, any two objects will fall the same way, it's still just kind of, to me, like amazing when you see it for the first time. The original video like this was the people who first landed on the moon brought a hammer and a feather and just dropped this. So this astronaut on the moon just drops a hammer and a feather, and you can see them fall together. But it's a really grainy video, and so this is cool because it's new, it's perfectly clear, and they drop it from way, way up. So okay, let me pause this.